T-shirt. It's a little bit small. It's an XL. So. All right. So, hope you guys had fun at our party last night. And we'll go ahead and get started with our first talk of the day, malware software armoring.
All right, everybody, thank you very much for coming. It was a great party last night, and it was a wonderful 9 a.m. this morning getting up. So I'm impressed there's this many people here. It's a true testament to everybody's character. My name is Danny Quist. I'm a co-founder of Offensive Computing. I'm also a PhD student at New Mexico Tech. Also do reverse engineering, exploit development, and part of CDC NSF.
Hey, how's it going? I'm Val Smith, one of the co-founders of Offensive Computing, work on the Metasploit project, CDC stuff, etc.
Okay, so we wanted to talk a little bit about what offensive computing is. How many people here actually use our site? Anybody use it? Okay, good. Wow. We're glad to see it's being used. So those of you that don't use it, we are a free and open malware analysis site. We have sort of a blog format where people can contribute analysis of code as well as malware samples. So our big claim to fame is that we give away all our malware, one at a time, of course. So David Tell said some nice things about us when we were starting. We also do some business services, so if you need malware, anything, let us know. Okay, so, all right, so what we're going to do is we're going to talk about the problem of disassembling malware, or unpacking, as we'll call it for the rest of this talk. Software armoring is another term that's used in academia that we sort of picked up. This comes from covert debugging. Basically, you want to be able to debug a piece of software without being caught. We're going to show you two methods. The first one is a dynamic instrumentation method. The second one is the OS page fault assisted debugging. And then we'll show you our application of it, which is a generic auto unpacker.
Okay, so first, what are the problems that we're trying to solve? Basically, doing malware analysis is pretty crucial for adequate defense because when you take apart a piece of malware, you can create signatures either for your IDS or if you have other tools to help you block it. Understanding the attacks that are out there and what they're doing to your networks and to your systems, you can get a lot of this understanding from reverse engineering malware. You can data mine trends and what's going on out there with the attacks and how they're improving and the different techniques. And then you can sort of determine if attacks you're seeing on your networks are related, are there variants of each other, or are they completely separate. So the problem with this is that malware authors don't want us to be able to do this. They want to stop us from understanding what they're doing so that we can't defend against it. They do this in a variety of ways, and we're going to go pretty in-depth into all these different methods that they use, but we're going to sort of give it an umbrella term of packing. And packing hinders our analysis. It makes it hard for us to understand these binaries. They use a whole bunch of anti-analysis techniques. Packing also makes it difficult to automate our analysis techniques. So if you're on a large network that sees tens or hundreds of pieces of malicious software coming in a day, it's going to be very difficult. The only way to handle the large amount of the threat that's out there and how it's increasing is really to automate your analysis process. So the internet is basically a huge number of malware samples. There's tons of malware out there running around. Our site has almost 300,000. More pieces of malware are coming in every day. And analyst time is very expensive. It can take hours to analyze a complex sample, maybe even days. So the only way to keep up is to automate this, but packers degrade our capability to do so. So we need to come up with a way to automatically decrypt or deobfuscate malware. So there's some previous work out there that people have been doing which actually help with this problem a bit. Shadow Walker, if you've seen any of the Black Hat talks, this is more of a rootkit technology, but it actually applies fairly well to the problem. There's several others, but especially we want to talk about Olibone. That's probably one of the most related to what we're doing in PolyUnpack. And a lot of thanks to Joe Stewart because his tool really inspired us to start looking in this direction. I know Havar's doing something too, but he hasn't released anything yet, so we'll see. The problem with these available solutions, though, is that they're not really set up to be automated. Some of them are GUIs, or they're to be integrated with OllyDebug or other tools like that, so you still need an analyst there manually going through these steps. Several of them are signature-based, or they have a smaller percentage of success than you might need if you have a lot of complex obfuscation going on. A lot of times they can be slow, and none of them really address the whole problem that we're looking at. So what we're going to show you today are techniques that we feel are a crucial step in automating this process of deobfuscating and decrypting malware. We'll demonstrate some example code that might help you in implementing your own tools. And then some ideas on what may be next for us to do.
Okay, so what we're not going to show, this is research code, which is another way to say it doesn't work. Well, it works in a controlled environment of our laptop right here, but we released our dynamic instrumentation version, and that was intended to be a proof of concept. So it's a little rickety, so I just want to get that out ahead of time. And here's a definition of proof of concept in case.
Yeah, I mean, it's fairly complex to do this, and so right now we're not releasing something you can go double-click on setup. You have to do quite a bit of work to compile the code, put it together, and get it working.
Right.
So the implications of this is that automating analysis is now within our reach, we believe, because of this auto-decryption that we're doing. Obfuscation is no longer the major obstacle to automating analysis using our techniques, hopefully. This gives you the ability to process thousands of files, which is good for us since we have many, many samples. Malware authors are going to have to step it up. No technique is foolproof, but this is pretty good. And you can start developing advanced tools. Okay, so now we're going to talk a little bit about software armoring and what I'm really talking about when I say obfuscation, packing, etc. So this sort of came out of shareware and people protecting their intellectual property from being pirated, but a lot of people use this now to prevent analysts from understanding their tools. So they use things like packing or encryption, which basically obfuscates the code. There's SEH tricks. There's ways of making the code crash so that it deobfuscates itself using the crashes. Virtual machine detection. A lot of analysts use virtual machines to look at the malware, and I've seen a lot of samples out there that will detect this and either destroy itself or try to crash the virtual machine or do whatever. Debugger detection is probably one of the most prevalent, where they try to detect that you're running their tool in a debugger and stop you. And then the shifting decode frame. Okay, so a little bit more about what packing is. Self-modifying runtime code. So basically these are small stubs of code which understand how to decrypt or deobfuscate the rest of the code in memory. WinZip can almost be considered, like the self-unzipping version of WinZip could be considered a packer in a way. So these little stubs will decompress or deobfuscate the main code in the executable, restore things like the imports table. So packers can play tricks with PE files or portable executable files. They can mess with the PE header settings so that your tools will crash, but Windows thankfully will still run the portable executable, and then obscure other parts of it. So this is sort of what a normal portable executable file looks like. And you can see over there to the right is some assembly, and that's what normal assembly will look like. After it's packed, it's going to look something like this, which really doesn't give the analyst any help in understanding what's going on here. Okay, so the next technique that they use is virtual machine detection. There's a whole variety of ways to do this. We released a paper 2 years ago on how to do this in VMware. Ours is generic across different virtual machines. Joanna Rukowska released a technique and several other people. So basically these are instructions that you can check or set to look for whether a virtual machine is running. The next technique is debugger detection. So Windows actually includes an API call for us to do this. It's called isDebuggerPresent. And you can just call this in your code and detect whether or not there's a debugger. Thankfully, a lot of tools have plugins, like OllyDebug has plugins to get around this. There's an assortment of other ways to do it. You can check timing. There's a variety of things to detect debuggers. You can look for breakpoints. You can check some yourself in memory to see if you've been modified. A lot of times this is what happens. You can do hardware debugging detection, where you check CPU flags for certain signatures or settings that indicate that you're running in a debugger. People used to use soft ice a while back, which was a pretty good kernel debugger, and there's pages and pages of methods for detecting soft ice. Some pieces of malware will use SEH tricks. This is the structured exception handler. Some people use this for writing exploits too. Basically, it's used to handle errors in running code. Malware will use this to unpack itself. So what it'll do is it'll generate an exception that points to the next chunk of code that understands how to deobfuscate the rest of the code. The problem with this is it causes the debugger to think that the program's crashed, or that the exception is for the debugger. And so in some cases the debugger will die, or you won't really be able to advance efficiently in the code. We've seen some malware actually do a divide by zero in order to generate these. Shifting decode frames is where the packer or the obfuscator will decrypt a small part, a small piece of the code, run it, re-encrypt it, and then move on to the next piece. These are probably the hardest to deobfuscate. It's very hard to defeat. It's similar to the way PatchGuard works.
Okay, so one of the ideas we got upon here is that it's almost as cheap to use and effective to use hardware for your analysis. It's almost as cheap, and it's nearly impossible to detect, because this is the customer for all the malware authors. This is what they're doing. So there's a couple tools that I want to go over real quick that we found, and we'll talk about that. So cost comparison. Last night I looked up on Dell what the absolute cheapest little mini crap box I could find was. So brand new, it's $349, and it includes an XP license in it, provided you pay for software. And then a copy of Deep Freeze to emulate the restoration feature runs about $45, compared to VMware, which is $189 and $278. So this is a rough estimate of cost. As far as replicating VMware snapshots, which is one of the more useful tools, I wanted to put a plug out for Phoronix Deep Freeze. I have no monetary interest in this company, but it's been a pretty good tool for me. So basically, it implements copy on write protection in the kernel. It's not perfect and it's hackable, but I haven't seen anything specifically target it yet that wasn't specifically meant to say that this code was buggy. So malware samples themselves haven't actually got it. But another thing that you should do is actually disk image using DD or whatever methods you have available as a last resort. Other good tools, the Firewire kernel debugger. Those are always fun. WinDebug. Thank you, Microsoft. This tool is awesome. And this new program called
Cicer.
I don't actually know how to pronounce that. But this is a soft ice replacement, or appears to do much of the old functionality that you can actually legitimately buy. But you have to be careful with all these because they're still detectable. Okay, so the basic Achilles heel of a packed or protected piece of malware is that if it executes, it has to be unpacked. That, meaning the Intel CPU can't actually execute gibberish code.
Okay, so I'm going to go a little bit over manual unpacking so you can see how labor intensive this work is if you haven't done it before, and see why he's automating me out of a job. Okay, so the way an unpacker works basically is that, and by unpacker I mean what's actually in the piece of malware unpacking itself, is that there'll be a write to an area of memory where it's beginning to decode. This memory will be read from and executed. There'll be more writes to memory. And so this is sort of a process we can track. Like Danny said, the CPU can only execute real code. If you send that pile of numbers that we saw earlier in an encrypted binary, the CPU doesn't know what to do with that. So at some point, it has to be clear. And so it's all related to timing. If we can get there at that point when the code is clear, then we can unpack it. So there's a few stages to the manual unpacking process. First thing you got to do is identify what it's packed with if you can. There are more and more samples coming out that are using custom packers that are written that aren't released. There's some tools that we'll talk about in a minute on how to detect this. The next and probably most important step is discovering OEP, or the original entry point. What this means is the point in the code where the original program before it was obfuscated is. If you can find this, you're good. The next thing you do once you find the original entry point is dump the process memory to a file. This is a file that you can analyze with IDA or any other disassembly tool. Sometimes you have to fix up the file. There may be problems with the PE header or the import table. At this point, you should be able to analyze the file. So, on the first stage, identifying what the packer type is, there's a whole bunch of tools out there. PEID is probably the best one. It has a huge database of signatures. We worked with the Metasploit guys on modifying MSF PE scan to do this. And then Aero Carrera's tool has had some patches and modifications from us to do this as well. You can manually look at the section names in some cases and see what it's packed with, and I'll show you what that means. There's a few other tools out there, but they're not as good as PID or some of the others. So this is a screenshot of several tools looking at a piece of malware that's been packed. PID is in the middle, a little gray window there, and you can see in the bottom, hopefully it says UPX. In the black window is MFS PScan. There's a screenshot of our site up there, and on the far left you can see an IDA UPX over and over again. That's looking, that's an indication that it's packed with UPX. Okay, so for the next stage, trying to find OEP. Thankfully, if you use OllyDebug, there's a whole bunch of scripts out there for most of the generic sort of low-end packers that can help you do this. A couple of websites I recommend, especially OpenRCE, Pedro Amini's site. It's a great resource for this. And there's tools out there, but a lot of these tools are signature-based, meaning that if the tool doesn't know about the packer, it can't do anything for you. So here's just a screenshot. We'll show a demonstration in a second. Okay, so the next stage in the process is dumping the process memory to a file. There's a few tools for this. I like OllyDump and LoadPE the best. Sometimes one doesn't work quite right, so I use the other one. You could write your own custom tools, which we've done in the past. This is basically some pseudocode of how to do it. Open up the process, read the memory, write it to a file. It's pretty straightforward. And here's a screenshot of some tools dumping it. Okay, finally you're going to have to fix up the file to make sure that it's actually legible. Imports are probably one of the most important things when you're analyzing malware, because it's a list of functions that the malware is using from Microsoft DLLs and APIs that can give you an idea of its capabilities, like can it write to the registry, can it delete files, what does it do? So here's a screenshot of a couple of tools. Really, there's a tool out there called ImportRec. That's probably the only realistic tool you can use for doing this. I've seen a few other things, but they don't really work. Okay, so at this point, you should have clean disassembly. You should be able to see the imports. Functions should make sense. There's strings, all the stuff you need to analyze the malware. One good point is we're not releasing a piracy tool. Some people want a binary that matches byte for byte the original before it was obfuscated. And really, that doesn't give us much value in malware analysis. If you're trying to pirate software, that's great, but our tools won't help you do that. Well, having a byte for byte copy is good.
Right.
Okay, so this is a screenshot of imports. The middle window there just shows what clean imports look like. Okay, so we got a movie. All right, I can't actually see the movie on my screen, so I'm going to lean over a little bit here. All right, so basically I've dumped this packed file in PID to identify that it's packed with UPX. Now I'm going to run it to show it actually functions. Here in TCP view, it's listening on a port. This is some cheap Trojan we found out there. So we're going to open this thing in IDA so you can sort of see what an obfuscated file looks like. You can see IDA gives us an error right away that the imports are screwed up. And normally in that names window, there's a bunch of names of functions and stuff. It's pretty much blank. The functions window is blank. So this isn't very valuable for analysis. The imports this is sort of standard malware imports. Normally there should be like 100 things in here, there's only a few. So that's an obfuscated binary. We can't get much information about what it does this way. So we're going to dump it in ollie debug, which also gives us an error saying, yeah, something's wrong. We're going to run a script. UPX is like the most common packer, and it's pretty simple. So this script basically executed the program and dumped us at OEP. Note the address, 40BB09. That's the original entry point address. So keep that in your mind if you can, because we'll need it later. So now we're going to dump the process memory to a file using load PE. So that's dumped. And we're fixing up everything, making sure it's okay. Here's import reconstructor, import rec. This tool is going to help us rebuild the import so we can see what the capabilities of this file are. Import rec is sort of like black magic. You have to really fiddle with it to get it to work. But right now what it's doing is it's enumerating all the imports it can find in memory for this process. And then it's going to apply them to the file we dumped earlier. Okay, now we're going to open this dumped, deobfuscated file in IDA. And we should see a totally different view of it. So this time we don't get the same error when IDA starts up. Blue means code. So basically if you start seeing blue, it means you have good valid disassembly. And here we have imports where before we had nothing. The names window is populated. So this is an example of a simple packer and how you go through deobfuscating it so that you can analyze the malware. We got all the functions. We have actual disassembly that makes sense. You can see a bunch of functions here. So that's that.
Okay, so what? All of these, this is just a manual implementation of watching for a write into memory and then an execution into where that memory was written. That's the algorithm that are implemented in all these bugs here. Our point is that there should be a generic way to debug or an easier way to actually get this information out. So we need something that actually modifies the operating system at the fundamental level. Basically, it should be generic, work across all executables, efficient, good, and not degrade your system too much when it's not running, and as much as possible be undetectable and extensible. So we'd like to script all this up. So again, the algorithm, track all the memory that's written. If you see an execution into that memory, it's unpacked, right? That's a good candidate OEP. So the things that you have to be able to monitor are memory writes and memory executes. And next thing we want to do is automate the process. So there's a general method called dynamic instrumentation. This basically allows a running process to be monitored. The program that we chose to implement this in is Intel's PIN. Don't ask me what PIN means. I'm still trying to figure it out. If anybody knows, shout it out. But this uses a just-in-time compiler, very similar to Java, to actually instrument the code. So basically, you can get a variety of different controls. You can control execution at the instruction level. You can look at memory accesses, and you can also look at basic blocks. So you find process, attach, and detach. So if we take our example code here, our nice page of assembly, this is what it looks like normally executing. And what PIN does is it'll actually insert instructions before and after each execution. So the modified instructions look like this. This is just in our original code interspersed with the new the PIN instructions. So what our implementation does is that we monitor all the memory writes and insert them into a hash table. And if we get a hit on that hash table during execution, we call that a candidate OEP. So the results are, it's pretty successful for the most commonly used packers. Essentially what PIN does is it inserts itself into memory. So as if the process does any self-introspection, it's going to find PIN and die. But we found it works on roughly 70% of our collection. And here's a nice pie graph of our collection.
You can see UPX is the most common one.
Right. It works on ASPAC, FSG, P compact, and UPX. The way that we tested this is to create a simple Hello World application. We mapped this out in a tool called Orias's GDE, which is Go Visual Diagram Editor. If anybody's used GraphWiz, it's a version that works on more than 10 nodes. So this is an actual Hello World application in Windows. Each one of these little tiny unreadable boxes actually contains a memory address, and you have to trust me on this one because it's hard to zoom in. But what's neat is it kind of makes a pretty picture, and basically what I was trying to do visualizing this is find the unpacking loop. So throw a shmoo if you want to edit, if you can identify it. Okay. But it's right down there at the bottom. Basically, this is a tightly compressed, adjacent located list here. And if you look back at the original slides, it's down on the bottom right there. But it really jumps out at you. So this was a good proof of concept of the algorithm that had been in a couple papers. We manually identified all the addresses that we found. The graph there, you can see the clustering and actually zoom in on the unpacking code. And what's nice about PIN is it allows you to detach from a process once you've attached. So there are some problems with the dynamic instrumentation method. First of all, it's extremely detectable. Memory checksums, it shows up. Signature scanning, it's going to show up there. It's difficult to use, and really sorry about that. It was just a proof of concept code, but the code that we published at Black Hat, some people had trouble with this. But basically what we want to do is extend this to work generically and non-detectably. The other thing is that if you're inserting instructions before all the other instructions, it's going to slow things down considerably. So we need something faster. So the solution that we need to go to is a core operating system component that monitors all memory, intercepts that memory access, and logs it. And it would be really nice if it was a fundamental part of the operating system so we didn't have to worry about being detected. The method we chose is to overload the memory management unit. So we're going to go into real quick how virtual memory works on Intel, but each on modern operating systems. So Intel has a method where each process can have its own memory, and that's called virtual memory. And the idea is to keep other processes from being able to read each other's information. So this virtual address needs to be translated to a physical address, which is the actual address on the chip of RAM. A non-PAE mode 32-bit processor uses 2-page indexes and a byte index, and each one of those has its own page directory. So if we take a sample virtual address, the first thing that happens is that the CPU references that memory. So we split that off and find the virtual page number, which is the first 20 bits. The CR3 contains a pointer to the page directories, and that first page directory index is an index into here, and that gets you the page frame number. The next thing that happens is that the page frame number goes to the page table entry, and then the second offset is used. And then finally, you actually get to the page that's in memory, and memory is pulled out. So this process is usually performed by hardware in the CPU. Each one of these data structures back here has various permissions, whether you can write to it, whether you can read from it, execute from it nowadays, whether it's present, and this special field called a user mode. And by user, what Intel means is the operating system. So this process is a little bit slow, and to speed that up, another hash table is implemented in hardware called a translation look-aside buffer. So this is a major source of optimization in modern computers. So the hardware resolves as much as it can of the address as it can. If it gets to something it can't handle, then it invokes the page fault handler. So for instance, if you have a page of memory that's not loaded in RAM, or it has incorrect privileges, or it's loaded but it's mapped with demand paging, or it's not legal. Like for instance, if you dereference a null memory address or a string of 41, 41, 41, that typically invokes the page fault handler. So it's all indicated by special fields. Intel goes further. They define two TLBs. The first one is a data TLB. This is when you actually access a pointer in memory. The second one is a instruction TLB. Basically, this is for quickly executing code. So the assembly to actually invoke the process of loading memory into the data TLB is just to dereference a pointer. That'll cause an entry to be added. For the instruction TLB, it's a little bit different. You have to dereference that memory, copy a return value into that, so basically come back from where you came, and then do a short call. And that'll populate the instruction TLB. This is just like executing code. So we wrote our tool called Saffron, and what Saffron does is it implements a hybrid page fault handler. And again, this was inspired by Olibone by Joe Stewart at DEF CON 14. We really like this, so thank you, Joe. We only implemented this for 32-bit Intel CPUs, and basically we replaced the Windows trap handler. And essentially what it's doing is logging memory access. So we have this diagram of how things happen. The first thing that happens is that we start with a virtual address, and the hardware tries to resolve it. At that point, if it's not valid, it kicks it over to the operating system, checks to see if it's in the disk, checks to see if permissions are correct, and if not, it returns the address or it returns the error. So our code fits right into that permissions code. And if any of you are looking to translate it into, I believe this is Mandarin, here's a pre-translated version of the slide that we found stolen. They were nice enough to translate the paper, but not our names.
Or even copy our names in English.
Yeah, or even, I don't even. Okay, so as far as the actual software architecture, page fault will come in on this left of the interrupt descriptor table. Saffron looks at it, determines whether it's something that we actually care about, and if we don't care about it, we kick it over to the Windows page fault handler. Otherwise, we talk to our user mode process that's actually monitoring this. The particular bit that we're overloading to cause the page fault is the supervisor bit. Basically, what we want to do is find the process's memory and mark the supervisor bit on everything inside of there. And then we want to invalidate the page inside the TLB, which is basically says clear your hash table of all your entries. Actually, if I could turn off caching on an Intel CPU, that'd be nice too, but I can't. So if anybody knows how to do that, please talk to me after. The next thing is that the tricky part is finding all the memory. First technique is to start at 0 and go all the way up to all Fs. And basically what you do is you can also iterate through all the pages, or you can look at the PE header and then just go to all the sections and mark those. So again, we're determining if we're a watch process or a piece of malware that we want to unpack. First thing we do is we unset that supervisor bit, allow it to be loaded inside of the data TLB, and then apply the supervisor bit again so we can watch it. The method that you use to watch for executions inside of the memory is via the iTLB. So Jamie Butler and Sherry Sparks call this the TLB desynchronization. So since there are two TLBs, you're going to get a separate page fault when the code tries to execute inside of there. And what you're going to do is you'll mark that as the original entry point, and that'll send a signal to our monitoring program to actually dump the memory. The results of this, we can see the reads, writes, and executes. We can tell what they are, which is sort of nice. We can see what's being executed. The reads and writes are transparent. The problem is that you can only see for each individual page, but as we'll show in the demo, it's actually pretty fast. And it's pretty accurate too. So it solves a lot of problems for us. So the SCH decode problem, where it's causing issues with the actual SCH process inside of Windows, is just completely sidelined. Memory checksumming, the process, we don't actually touch the process memory at all. So we get good dumps across this. Some caveats. It's Windows XP Service Pack 2. I haven't even attempted this on Vista yet. You have to turn data execution prevention off. I believe that Microsoft uses a similar method to prevent executions into code segments, but that's just me guessing at this point. The other one is single CPU. You have to disable multiple CPUs in the BIOS, and this is purely a coding problem. And it's 32-bit only. We don't really care about 64-bit yet because there's not really much 64-bit malware.
Has anyone seen any 64-bit malware yet? I haven't seen her.
Yeah. Okay. I'm sorry, what was it?
I was just joking. I said they're still working on 486 in Russia.
Oh.
Yeah.
What are you implying there? Okay, so our big announcement is that magically it works on VMware 6, which hopefully we'll be able to demo for you here. But if not, we have a movie. We watched Dino's presentation yesterday, and we're peer pressured into doing a live demo for you.
Yeah, it's just Shmoocon. Got to do a live demo.
Some other caveats is that you either have to have real hardware or VMware 6 or higher. Older versions, if you read the paper that they published in ASPLOS, the VMware engineers actually described their method, and they're playing the similar sort of tricks with the TLB that we are. So it breaks our stuff. So real hardware, as far as real hardware, you got to take proper precautions, and that's using deep freeze or DD or anything like that. And also we found that you can't have a kernel debugger attached because the Packer T-lock still detects a kernel debugger, which is really kind of neat of T-lock. But anyway, if you just detach the FireWire debugger, it works great. Okay, so we'll try and do a live demo here.
This was working, and then it wasn't working, and then it was working again. So if not, we have a video where it definitely works. All right. So what we've got here is a VM, and it's loaded up with Saffron. We have a few samples of NetBull that are packed with different packers. We'll try T-lock because it's one of the more complex ones. So what I've done here is put it in PID to sort of prove that it's actually packed with T-lock. Oh yeah, sure. You guys see that okay? Yeah, I know it's not going to be great. Okay.
You can also, there's plenty of room up here if you'd like to.
Yeah, so we're using this tool, or actually why don't you describe it? You tell me what to do, I'll run it.
Okay, so basically what we have is a kernel driver here, and we want to install it into memory. So we use the InstDRV, which we learned from Jamie Butler's rootkit book. We've looked at PID, determined that it's T-lock, and if we copy the original file over to IDA, we'll let that chug there for a little bit. Basically what we're going to see is that you get this a warning about imports being destroyed, so we're going to click through that because we have no fear. And it's going to continue going, and we get this nice function which looks like a whole lot of nothing. There are no functions available. The imports are pretty much non-existent. The strings window doesn't have anything real useful there. So the conclusion is that this is a packed file. So we're going to go ahead and close this. And the next thing we're going to do is go to Saffron, which we have a command line for, and we're going to cross our fingers and go ahead and hit that. Okay, so we get a candidate address here, and it looks like
it crashed.
Looks like it was a good demo, and it crashed. So we tried. I'm sorry, but we do have a demo of it running on. It's still a little picky about raw hardware. So what I'll do is.
Want to see me blue screen it?
Yeah, I don't think that's necessary. Okay, so. Sorry about that. We sort of expected this to happen and we tried it about 400 times yesterday, marveling at the magic that it was. And
there's still something going on that we don't quite understand about the way VMware interacts with the TLB. which makes this unstable on VMware. On raw hardware, it's completely stable.
Yeah. Okay, so this is a video of raw hardware, and basically we're going to redo this whole process. We see that we've got the PID here. We've got TLOC and UPX versions of this. So we'll go ahead and load this up in Ollie debug and use the method that Val showed earlier, where we're going to run it with this Ollie script here to basically unpack or find the OEP. And just for consistency, so the address there is BB08, if you watch that. And just for consistency, we use the same version of the virus, which was netbull. So again, we'll load the driver here. Get that going, and then actually run Saffron against it on the TLOC version. And what happens here when it doesn't crash is that you see this actual address, BB08, and we see an execute inside of that memory region. So now what we'll do is each time we see a candidate OEP, we actually dump a file. So we're going to drag this over, open it up in IDA. Imports are still destroyed. Well, so this is the original version here that we tried to look at. Okay, so the original version has no names, no functions, no strings. Well, it has strings, but they don't look very useful. And the flow graph is very boring. Okay, so let's close this, then open up the new version of, or the unpacked version, one of our dump candidates. So we'll copy that over. And what we can actually see is that as IDA executes, we're getting more functions. It generally seems happier. The functions are being filled out, so it's able to analyze a binary and find the C++. And up top, we can see that the graph or the visualization shows us that there's more code that's actually there. And as far as like the cross references, you find that, and you get the unpacked version.
Working now.
Okay.
You want to see VM Protect?
Yeah. Okay.
We can try this.
Val got the live version working again.
Maybe. I just got it to unpack VM Protect, so we can try it again and see what happens.
Has anybody here tried to unpack VM Protect? Or
VM Protect is this Russian packer that carries a virtual machine inside itself to unpack itself. So it's really hard to deal with. All right, so I've already loaded the driver and everything. Let's. I know you probably can't see this so great, but we're running saffron-file, then the VM Protect version of netbull.
yay.
So now we should have some unpacked files here. So basically, I mean, we have the same dump of VM Protect, and you can see that we use the OEP address in our dumps so that we know which one is more likely to be the good one, and that's the same OEP we keep finding. I'll open an IDA so you guys can see what it looks like. It's going to take a minute.
So the multiple candidate OEPs are coming from each time you hit executable section?
Right. Each time we hit an execution inside of a previously written memory address region.
Sometimes a rule of thumb is you can go by the last dump, because that's generally past where you need to be. In this case, since we manually unpacked it first to test it out, we knew what the real OEP is, so that's why we're going with that one. But you could take the last dump, and in general, that'll be good.
Okay. And so as you can see here on the live version, we've actually unpacked VM Protect 2 generically without having to actually step it through a debugger.
So the strings look pretty good. We can even, you know you have good disassembly when you can chart xrefs or even follow them. So, you know, we have completely usable disassembly. The strings, I mean, we even got, here's where it does its run key, so it starts on boot. Here's the guy's name, stuff like that. So it's pretty well unpacked. The imports are good.
Second time's a charm. Okay, well, while Windows is figuring that out, let's see. Oh, no. All right. So some of the future work, we released the initial version of Saffron at Black Hat. This is the dynamic instrumentation version based on PIN. This was some of the original. This is based on their code, which has a strange Intel license, meaning it can't be really used in any sort of commercial form. But we're still working on a drag and drop unpacked version of the Saffron kernel, and Danny's learning kernel programming, as you can all tell. So we're going to integrate this into offensive computing, and it'll be ready any day now. As far as questions or further information, offensivecomputing.net. But I'd like to say thanks to Lori Liebrock, Houdini, Escape, BugCheck, Skywing, Tybo Dell, Uninformed, and Vax. Everybody was really helpful in helping us get through this. So,
Thanks. I think we still have a few minutes if you guys have any questions or want to talk about anything else.
If you've got strange Packers, feel free to come up and we'd like to try them. So, yes?
At the beginning of your presentation, you talked a lot about automating the process completely.
Right.
With thousands of things, this thing you showed us still needs significant analysis.
Yeah.
Can't command line, you didn't cover any of the sort of automation.
The automation for this would be to put a while loop around that command line and then just feed it new pieces of malware each time. So, something like that, yeah.
Our website actually automates a lot of the analysis process. It just doesn't automate the decryption part, which is what we just demonstrated. So the decryption part is really the hardest, most labor-intensive chunk of it.
If you want to ask questions, come up here or talk to somebody.
Get a copy of your presentation if I send you an email.
Yes, it's up on our website.
Offensivecomputing.net.